Alright, so we're back for more. We got another mechanism to talk about with nucleophilic aromatic substitution. And this mechanism is a bit strange in a couple ways, and I'll mention a little bit more as we go through. But here's the basics. If we have Mr. Aromatic ring, and let's say we have something like a chlorine on there, it should work fine with a bromine too. And what we do is we put this in the presence of sodium amide and ammonia. And we let this reaction go. What we will get is this product here. I say, oh, that's nice. That seems useful, right? We can add an amine in there, and that could be useful for us, so we don't have to go through the nitration and all this other kind of stuff. Sure. Say, okay. Now we do a slight change, okay, and we do this, and now we get this product, right? And we get this product in about a 50-50 ratio. Okay, so something is going on here then. So let's look at a new mechanism. So what's going on here? We'll call it an alkyne mechanism. Now, what I would do here is ask you guys to go through and take a look at our reagent setup. Where have we seen sodium amide and ammonia before? And I'll give you a hint, all right, it's up there. Okay, sodium amide and ammonia is a very powerful base, and we've seen it used in the past where we can form alkynes, right, where we do two subsequent eliminations of a vicinal or a geminal dihalide, right? And we can form an alkyne from there. So if we had something like, this, okay, and right, we would end up forming our alkyne. Good? So what is the mechanism for this, right? Hopefully you guys remember that. We're doing a couple of subsequent elimination mechanisms where we grab the hydrogen next door, we form the alkene, and then we form the alkyne, right? So if we want to think about this, right, the intermediate here, quote, quote, intermediate, would be something like this, right, where we have an alkene with a halide on there, right? And then we do another elimination, right? And we get to our product. So what is an aromatic ring? Well, an aromatic ring, well, let me draw it a little bit differently here. Well, here's what this aromatic ring is. Do you guys see how basically this setup is the same as this right here, right? Where we have a halide attached to, right, a double bond, right? So we have a vinylic, right? We have a vinylic halide. Although it is different, right? One's on an aromatic ring, and there are other considerations to have here, right? But what's going to happen, right, in this case is, erase that, right? What happens is our sodium amide, which is a powerful base, okay, it's going to come in and kick off, right? It's going to come in and kick off that chloride, okay? And so here is our proposed intermediate. Now, what is unusual about this? Well, what's unusual is we've got a triple bond here, okay? Now, this isn't really a triple bond in the same way that this would be a triple bond up here, because this is a strained system, right? So to be able to get a triple bond, we have to have parallel p orbitals that overlap, right? We have to make 2 pi bonds, but the orientation of the ring here doesn't allow that to happen, right? So what I'm saying is these green carbons up here, these are sp hybridized, right? They're 180 degrees, which allows for the 2 sets of p orbitals to overlap to form bonds, okay? But we don't have that down here in the aromatic ring, right? These are not 100, right? The hybridization of those black carbons in the ring there are not 180. And so we can't get the exact same overlap to make a triple bond, which means this is a couple of things. One, this is a really strained system, okay? Which means it's very reactive. And it's not really a triple bond in the sense that we might think of a triple bond, right? It's somewhere in between, okay? It's a triple bond in the sense of the orbitals that overlap are forming a kind of bond. Well, anyway, it doesn't really matter, right? For our purposes, we can just consider it a triple bond, but it's kind of not true for that to be the case. Okay? What I do want you guys to recognize is that this is a very reactive system. Okay? It's very reactive because of the strained ring system there and that weirdo pi bond that's going on there in purple. Okay? But once we generate this benzyne intermediate, our buddy ammonia, well, let me draw this out a little bit differently here. Boom, 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 right? Our buddy ammonia can come in and either hit here, right? Or, let's do green. Or there, okay? And when it hits there, it can push up the bond, or when it hits here, it can push up the bond. But it can hit either of those black carbons in about a 50-50 mix. Okay. So what happens? Well, let's draw this here. We'll just pick, well, I don't know. Let's pick the blue here because I want to draw in blue today. Because I'm an adult and I make adult decisions. Okay, we got this, right? And so if we follow the arrows in blue, so I'm just going to erase the green there just to kind of clean things up, right? That means we stick a lone pair and a negative charge here, okay? And I think you guys can see what's going to happen, right? Very quickly, we have a intermolecular shift here, the acid base, right? Hydrogen getting swapped around there. Okay. All right. So that's the mechanism, right? The same mechanism. You could go back and draw it in green to get to the the para derivative there, right? So that's basically the mechanism that happens here with the alkynes. There are a couple of considerations, right? Whether you have electron withdrawing groups, right? When you have electron withdrawing groups, there is a preference for certain attacks at certain positions and all this kind of stuff. But I think that's a little bit beyond what we need to talk about for this course. What I do want to say about this is that there are some common setups. You'll need a halide because you're doing an elimination. You want to have, right, kind of, let's say, unactivated rings, not deactivated rings, but, just kind of, I don't know, neutral. It doesn't work very well if you have a this reaction doesn't really work very well if you've got a lot of electron density in the ring itself. And you can kind of think about why that is and what the purpose is. I'm not trying to be coy about this. It's just, I guess, the reason why I'm just trying to, hop around here is that I don't really see much purpose in this reaction. I've never really used it for anything. it's not selective, right? We get a mix of products, so I don't much see the utility in it. But there are some interesting parts to it. There are some nice products that have been formed with us along the way, but just for our undergraduate course, right, I don't really see much use in this. Our other mechanism of this nucleophilic substitution is much more useful for us in terms of synthetic, right? But here we go, right? So one last note, sodium amide and ammonia, right, is probably one of the more common reagents to set up this reaction. You can use some other strong bases like sodium hydroxide, right? Like sodium hydroxide, but you got to heat it up. The sodium amide ammonia you can run at lower temperatures. So there are some changes with some things that you can do in here. But like I said, that's pretty much all I've ever seen for these. I'm sure there are some other bases that you could use, like t-butyllithium or something like that. But again, right, there's quite a few variations of strong bases we could use for a lot of these things. But yeah, that's kind of the end of this. That is the last mechanism here, this alkyne mechanism. The last video that I'll do for this chapter, we'll talk about some random reactions that we kind of skipped around along the way over, and then we will call it a wrap on the aromatics. Okay, so nice short video today, just one simple mechanism, just one simple condition here, and we are good to go.